Alright, now we're going to talk about subtraction using a report carry adder. On the previous video, we look at the structural design of report carry adder, and we use that to sum, for example, to sum x plus y. So all of these were positive number and sign. Now we're going to look at the subtraction of using report carry adder. So for example, in the summation we had, for example, x was 7, for example, so 7, and the y was 1. So when we sum this, normally we should get so it's 0, 2 carry 1, 0, 0, 1, so it is 8. So this was our x, y, and sum. Now we want to do the same thing, but we want to subtract. So normally we'll do, for example, if you have 7, x 7 minus 1, so this is going to be 0, 1, 1, 0. So this is 6. But this is how you normally do for yourself, like a normal mathematic. But if you're going to use computer, you must know how can we represent, because this is one is minus. How will you represent this minus number? So we must know how to represent sign numbers that are minus. We call it sign. Negative numbers can be represented in 3 ways. So there are 3 ways to represent negative numbers. We have what is called sign. So it's sign magnitude. Sign magnitude. So we have sign magnitude. That is the one way to represent number. And then we have first complementary, first complement, and we have second complement. So for example, if you take this is binary number, if we have binary number 7, for example, so it's 1 1 1 0 1 1. This is 7, and in binary you will present the same way, 7. So you have 0 1 1 1. In first complementary this is the same, because all those are positive numbers. And second complementary 7. But if you want to represent this minus 7 here in sign magnitude, so that's why you have magnitude, which are this here, and you have a sign. So we here all of them are 4 bits. So the last bit represent the sign. So if the last digit here is 0, so it's positive. If it is 1, it's negative. So if it's 0 equal to positive, 1 equal to negative for the sign magnitude. So if it is minus 7, you present minus 7 1, that means minus and 7. So this is most easiest way to present, and is user friendly too. But when you come to the first complementary, which is also the negative number you want to present minus 7. The equation for this is 2n minus 1. So if you want to find the negative number of the first complementary minus the number that you want to the magnitude that you want to represent. So, and then it must be equal to 4-bit as well. So, and then generally you will find out that this is just, you must flip, I'll not go to the proof of that, it's just to flip all the bits. So if it is first complement, so it's gonna be 1 0 0 0, and for the second complementary, that one is for example, the number second complementary is equal to first complementary plus 1. So this one you will find it, for example, so you can see this here, it have also a sign, it indicates it is a negative, and here minus 7 here is, so it is first complementary of this one plus 1. So for example, if it is 7, so the first complementary of this one is 0 0 0. If you plus 1, so it is 1 0 0 1. So this is how you find the first complement. So both of them are negative numbers, minus 7, but they are represented in different way. So the easy way to know if this one, for example, is minus 7, you look at this last digit here, which is minus, so this one is, for example, here is 1 2 4 and 8. So you take minus 8 plus 1, you get minus 7. So in computers, it's hard, it's impossible to do a arithmetic subtraction using sign magnitude. It has some drawbacks. So for example, minus 7, 7 minus 1, we should get 6. So let's see which number we'll get. So for example, we want to do here 7 so and we want to do it minus 1. So in computer, so if you do it plus, but we write here minus 1, so and then minus 1 in magnitude is 1. So this you have 1 0 0, this is negative, so it's minus 1, and then we do addition. So this is 7 minus 1, but this is a sign, so but we are doing a plus because this is minus. So since we're going to do a minus operation, so 1 plus 1 is 2, so it is 0 1, we have a 1 here, so it's 2 again, so it's 0 0, then you have 1, you have 2, so it's 0, and we have a carry out, for example, but this is meaningless if you look at the sign numbers, it's meaningless. Carry out is unused. So we can see here it says that 7 minus 1 is 0. So this is incorrect. Let's look at the first complementary again. So we're gonna do it again. 7 and then plus minus 1. So what is the first complementary of 1? So of our minus number. So minus 1 is written here because you have 1. So 1 is written like this, 0, 0, 0, 1, and then first complementary of this, all of them are 1 and 0. So it is 0, 1, 1, 1. So this is 7 minus 1. So here we have 1, 0, 1, and then we have 1, so it's 0. So now here it shows us we have 0, here it says 3, but let's look at the second complementary. We have 7 minus 1, and then how you do write minus 1 in first complementary? Okay, it is 1 is written like this. Second complementary of this, it is this one plus 1, so it is second complementary of 1 is, so you do the first complementary of, so you have 1, so it's 0, 0, 0, 1. The first complementary of that is 1, 1, 1, 0, and then you add a 1, so you have 1, 1, 1, 1. So here we have 1, 1, 1, 1, so which is minus 1. So what is the answer here now? So 1 plus 1 is 2, so you have 0, you carry 1. So 1 plus 1 is 3, so you have 1, you carry 1. Here you have 3 again, you have 1, I carry 1. And then here it's 0. And then you have, but it's meaningless, the carry out. So you can see here, this one, the answer is 0. Here it shows us the answer is 5. But here, it shows answer is 6. So we're going to use this second complementary to design the reciprocal adder. So we must do some modification. So we can use this one. So we know that in our reciprocal adder now, what we can do, if you have x and y, so you can say if you sum, if you want to do x minus y, the way you can do it, so you have x plus second complementary of a number, and we know is equal to x plus the second complementary is equal to the first complementary plus 1 sum. So this is the equation we're going to use to design our Adder Subtractor for reciprocal adder. We had this equation here. So how can we use this equation to do both addition and subtraction? For example, if you have a number of 4 bits, so 4 bits number, and then y here, our number y. So for example, if we have number 3 in bits, we know this, the second complement of this is the negative number. So the easy way to find the second complement is to look at at the first the first position that you have bit 1. So here we have a bit 1, and then we flip the rest. So here in here the first bit is come here, and then we flip the rest. So we keep the 1, and then we flip the rest. So it's 0 1 1, and so this one will give us -6, -3, and then if we have 0 1 1 0, so this is number 6. The second complement of this one, you look at the first bit that you have 1 here, and if is and the 0, you copy the 0 from the right hand side. So here you have 0 1 0 1, and if you have 7, let's take an example of 7. The first bit is here, we flip the rest, we keep 1, we flip the rest, so this is -7. And then if you have a 4, let's take a 4. So 0 0 1 0. Look at the first bit that you have 1 here, but if it's 0, you copy it. So 0 0 1, and you flip the last bit. So you can see here you have -8 plus 4 is -4. And then the first complement of this is just straightforward. This one is just flipping the number. So this from here we're gonna be 0 0 1 1, and here you can, for example, 1 0 0 1. So how can you use the same equation to do both of this operation here? So let's introduce XOR. This is very useful, and I'll show you how you can manage to do all of this operation with XOR. So you have an XOR here, for example, XOR, the truth table of XOR. So here, for example, you have 0 0, you'll have a 0, 0 1, you have a 1 1 0 1, and 1 1, it is 0. Now let's say this row here is our Y, and this row we name it as input. This we call it a controller. So for example, if C is equal to 0 and C is equal to 1, so let's take our first Y here. Our Y is, we have a 3 here. So let's find the first complement using this truth table here. Now, for example, let's see if controller is 0. So every time controller is 0, and we put this number through the XOR. So we have 1 1. So we go here, we have a 1 here, for example, and we have a controller is 0. Since controller is 0, so we always have 1, and then 1, controller is 0, you keep the 1 again. So you can see if you have a 0 and the controller is 0, you keep zeros. So you can see if C is equal to 0, we keep the number. Let's try if C is equal to 1. Okay, C is equal to 1 here, and we have our input of Y is 1, so we have 0, the first bit. the second bit is 1, and the controller is 1, so we flip it again, is 0, but the third bit is 0, but controller is 1, so 0, 1, we have a 1, so you can see it's flipped, we have flip, and we flip the last one. So you can see we can use this XOR to get the first complement. Let's try the number 6. If it's 0, we can see, okay, controller is 0, and this is 0, you can see we keep the number. If C is equal to 0, C is 0 again, and we have 1, so 1, 0 is 1, is 1 again, and 0, 0, 1 is 0. So you can see here, we keep the number. So C is equal to 1, and this number here, so 0, 0 and 1, 0 and 1 is 1. Again, 1 and 1 is 0. 1 and 1 is 0. 0 and 1, 0 and 1 is 1. So you can see we have flipped the number. So we have the first complement. So we can use this on C to get the first complement. So how will you manage to make a summation and subtraction using this equation? So we know that we can use XOR. So if you write sum, for example, sum x plus first complement, and then plus C. So we want to control this portion here. So if C is equals to 0, what we have sum is equal to x plus y plus 0. So this is equal to x plus y. But if C is equal to 1, what we have sum is equal to x plus, when C is equal to 1, is first complement plus 1. And then we know if you do this, we get second complement. Then we will have x plus minus y. So with help of XOR, we can do both addition and subtraction. So this is how we're going to do. So we're going to check this. And then one thing I want to mention, if you have, since this is 4-bit, we must know the length of, if you use second complement, the range of your numbers. So for example, the range of a number, if n is 4-bit, for the negative sign is minus 2n to the power of n minus 1, and for the positive is n 2n minus 1 plus 1. So then you have minus 8, and plus 7. So this is the range of addition and subtraction you can do if you interpret out that you are using a second complement bit number to represent numbers. This is the range you will have. You can just do addition and subtraction from 7 to minus 8 in your answer. So we see those two equations for that sum can do both addition and subtraction based on if we do x plus y, we XOR it with C, So we can get addition and subtraction. So let's just see here. The way we can connect this one here, for example, here we can just put XOR here, and then we can put the XOR here. So we can say this, our first, this is our X. So if it's 4-bit, it's connected here, and Y is 4-bit. So you can see here we XOR here before coming to the ripple carrier adder. So here we must have our controller. So based on if C is equal to 0, we have sum is equal to X plus Y. If C is equal to 0, and then if C is equal to 1, we will have sum is equal to X plus minus Y. So the way we achieve it, we connect this C here down here too. Then it will give, depend if it's 1 and if it's 0. And here we'll have our summation out. So we're gonna use in our program the same ripple carry adder, and here we'll have our carry out. So if you're gonna interpret this as complement numbers, this is not useful. So in the next video, we're gonna program this one in the Quartux Verilog, and to see how we implement this one on the program. And then here we have our carry in.